All right, guys, here we go. I think I got everything working. So, like I said, listen up, please. I'm going to jot some stuff down just to keep track of some stuff we're talking about. If you want to write this down, you can, but I'm not telling you you have to, okay? Pretty much all these main points will be like parts of questions on the study guide. But I'm just going to throw some stuff down up here. So that's your choice if you want to write this down or not. So the new topic today we're going to get to in a second is acceleration. Something we all heard of, right? But let's back up a little bit and remember a few things from last week about scalars and vectors real quick. We went over a few physical quantities that some of them fit in one category, some of them fit in the other. So out of speed, velocity, distance, and displacement, which ones were scalars out of the four of those? Yes. Speed and distance. Therefore, the other ones were vectors. What was the big difference, again, between scalars and vectors? Yes, so. Right. Vectors care about direction. Not just only slapping it on a final answer, but when calculating it, it considers direction as well. So we did some small calculations at the end of last week. We're not doing any more practice problems that just use V equals D over T. We just got to remember, if it's speed you're calculating, it's distance divided by time. If it's velocity you're calculating, it's displacement over time. And like we kept saying, those two could have the same magnitudes and be practically the same thing if during the trip the thing never changed what? Direction. All right? That couple of things we just recapped right there, probably the most important things to remember from last week. If you remember anything, those few things I just recapped. All right, so now moving along to acceleration. We haven't seen anything directly about it yet, but I think on one of the first study guides, you had to categorize a handful of scalars and vectors, and acceleration was on there. Who remembers, was acceleration a scalar or a vector? Yes, a vector, so it cares about direction. And I don't know why that's all coming up. Go away. Okay. So it's a term we all heard of, but before I define it, and we go through some of the differences that it could have, because there's several forms of it. How would you, in your own words, without looking at something, without opening up the physics classroom and just reading me, in your own words, how would you define acceleration? Or give me an example of it. Yeah, cool. Say that again. Changing speed. Good. That statement is absolutely true, and it actually, that statement alone actually gave us two forms of acceleration when we look into it a little further. So since Cole just said changing speed, and that's true, give me two ways to change speed. There's two basic ways to change speed. Give me one, yeah. Slow down, give me another. Speed up, all right? So there are three ways. Those are two of the three. These aren't specific notes, but just to keep track of some stuff we're saying. Slow down and speed up. These two ways, there's going to be a third, are the most important to us now. The third way is important. It's a way to accelerate, but it'll be a little more important in some sections a little bit down the road. You'll eventually see why. But these two that we just named, they both change acceleration. Acceleration is a vector, cares about direction. They both change it by causing a change in magnitude. I'm just going to abbreviate magnitude, all right? Because if you were in a vehicle and you sped up, you're going to see the number get higher, right? We said magnitude's a fancy name for the size, right? If you hit your brakes and you slow down, your number is going to get lower. But there is a third way, bless you, a third way to accelerate. Any ideas? I'll give you a big hint again. Acceleration is a vector. Yeah. Change in direction. And I'm actually going to write out, just so we can look at it, a brief word definition for acceleration. And if you look up acceleration in any, like, in the back of your textbook or whatever, I'm just going to abbreviate that, you would see it say a statement basically like this, that really, when you think about it, does include all those three things. So, in words, it's the change in velocity over a period of time. So looking at that all together, like the exact definition of it, and if you look at the three specific ways it could possibly happen, well, velocity is a vector, right? So vector has to have magnitude and direction. So if your velocity at any given moment, let's just use a vehicle again, if you're going 50 miles per hour north, if you sped up or slowed down, that would change the velocity because that would clearly change the number, right? Like we said, the magnitude part. But if you just took a turn, if you're going north and then you turn and you're going like northeast or something like that, you change your direction. And that's still accounted for in this definition. Because another way to change velocity is to change direction, since velocity is a vector. Everybody get it? So technically, you could have your car on cruise control. Cruise control only sets your magnitude and keeps it there, like at 65 or whatever. But you could be in cruise control and go around a bend, staying at 65, but you're still doing what around that bend, according to this? Accelerating, right? Now, the reason why that third way is going to be focused on more later is because as soon as we're done with this intro stuff and go into more problem-heavy stuff out of your book, we're going to be in 1D motion still. And that means, like, if we have car problems, they're not going to be allowed to turn yet, all right? So if we're stuck in one dimension and we just keep going one way, then the only way to accelerate is speed up and slow down. So early part of the year, these two forms are the ones you're going to see most used as an example for acceleration. When we get into 2D motion, especially circular motion, cars going around turns, or we'll study that, and the friction needed to hold them on a turn, stuff like that later on. So even if we're holding steady at our speed, if we take even the slightest turn, that's a change in direction, and that means that we're still accelerating. And we'll learn eventually that if we accelerate, acceleration isn't magic, all right? Something will not magically speed up, slow down, or change direction. Anybody have any idea what in general, causes an acceleration? This is going to be a big, super important idea later. Might as well throw it out there now. All right, let's take this ball that's right here. Not moving, right? Would anybody expect that magically that ball would just shoot up in the air right now? No. For something like that to happen, any object, doesn't have to be this ball. What needs to occur to, or what has to be present to make something like that occur? Flying up in the air, yeah. Good, a force. Let's just say force in general, all right? And that's going to be eventually part of Newton's main laws, that forces cause accelerations. Accelerations can't happen all by themselves magically, right? Everything will start connecting later on down the road. For change in direction acceleration, though, there's even a special name for it. Some of you may have heard of in the past. How many of you ever heard of the term centripetal acceleration? You might have come across that somewhere. That will be learned about more later. All right, that's kind of like this. We kind of call it the special form of acceleration because it's not like these two. All right, but so without getting into that other stuff, which we will get into later on too much, the ones we're going to care about the most right now are speeding up and slowing down. All right, real simple. But just be aware and keep in mind for now that change in direction is another way. All right, so let's now go over the units that we would typically use. Now, last week we were going over some calculations with speed and velocity. Some simple ones using the V equals D over T equation. When we solved for V, whether it represented speed or velocity, what were some of the typical units we were running into on our answers when solving for how fast or v, whatever way you want to say. Yeah, miles per hour. That's the one we're probably most used to. And while true, that's an English Standard Unit that you'll see early on, but soon we'll, especially when we get to the textbook, we'll start phasing out a lot of English Standard Units and getting into some other ones. So what's some other ones we ran into? Yes. Okay, kilometer, meters, centimeters alone, all by themselves, just measure what, guys? I'll give you something just in kilometers. What does that measure? A distance or a displacement, right? So it has to be like one of those over what kind of unit? Yeah. Right. Per second or per some kind of time unit, right? So the one we will be eventually most used to in here is going to be meters per second. So because of that, the most common unit, maybe not so much early on, they'll give you similar ones, but eventually for acceleration, our most common unit is going to be meters per second per second. Now, actually, typically, I'm just going to write or, because this means the same thing. We usually condense that, though. Mathematically, since it's per second, I could condense that into seconds to the second power. Those two things mean the same thing. So why in the world would I write it like this? Well, once in a great while, here and there, just to make sure you remember this from right now, just on one of our book problems, we'll throw in the unit meters per second. Most commonly, we mathematically condense it like this. But really, this stretched out version of it better explains what it means. All right, so let me give you an example. Let's say I walk I'm going to speed up from here where I'm standing to my wall over there. And I'll just make up some simple numbers, okay? Not realistic ones, but just simple ones we can keep track of. So right now, I'm at rest. I'm going to start speeding up at a rate of 2 meters per second squared. In other words, 2 meters per second. All right? So that means every second that passes, I speed up by how much? 2 meters per second. If I go from that wall to that wall, I continue to gain speed on the way there. All right? So if we know where we started at, what we're going to call initial velocity. If I start from rest, my initial velocity is what? 0. So after 1 second, if my going rate is 2 meters per second squared, that's what I'm going to speed up by. After 1 second, I'm going 2 meters per second, right? After another second, I'm going how fast? 4. After another second, I'm going how fast? 6. That's where the meter per second comes in. That's why it makes sense. All right? If you are given any kind of distance unit, like meters, kilometers, centimeters, even miles, even with English Standard, this is true, and it's divided by a double time unit, per second, per hour, anything like that, that's a representative unit of an acceleration. And we usually condense it into whatever that is per second squared. All right? But technically, any distance per time unit. You could even have weird ones, but would be still acceleration units. I could have like meters per second per hour. All right? Not a one you'd run into much, but it's valid because it's a distance per time unit. Okay? So that's the deal right now with the units. The next thing, yeah, question? Okay, that's actually what I was just going to get to. All right? That's all right. There's some misconceptions about acceleration, even if you know this stuff pretty good up to this point. All right? And let's just say I'm looking out the window right now. You're all looking at me, right? And I'm just going to tell you something that you didn't see. I'm going to say, hey, just look out the window. I just saw a vehicle accelerate at the acceleration rate was -5 meters per second squared. All right? That's all I said. I'll say it one more time. You guys didn't see it happen. Okay, I'll post all this. I just looked out the window. I have like an accelerometer in my head, so I can just look at things and know their acceleration rate. So I just looked at a vehicle go down the road, and its acceleration rate was -5 meters per second squared, or -5 meters per second. What are some things you can conclude about what I just said? Yeah. Okay. That's always the number one answer I get, or some form of that. But this is why I asked the question. Okay? It actually, you don't know enough information to say that. That's the answer I was fishing for, because that's a misconception. How many of you, and be honest, how many of you thought, even though you didn't raise your hand, because I put a negative on it, you assume that car must be going backwards? All right? That's what we got to clear up with acceleration, because most people do think that. I will say this. Even as the year goes on, even after what we're going to say here, most of the time it will mean that. But the point is it doesn't have to. So let me give you a little bit more. Here's what, to know the direction the thing's going in, if I just tell you an acceleration rate, and that's it. That's all I told you, right? I just told you an acceleration rate. To know which way it's going and if it's speeding up or slowing down, most importantly, you have to know which way the velocity was at the moment of acceleration in the first place. All right? So we will typically assume that positive means forward, negative means backwards. We're allowed to do that in general. But as far as whether it means speeding up or slowing down, it really depends. And let's just think of it this way. Let's use me walking right here like on a number line in 1D motion. If this way is the positive direction, and I'm walking this way already, remember we said forces have to cause accelerations a minute ago? We're not going to get deeper than that until we actually study forces. But with that in mind, if I'm walking this way already in the positive direction, so I currently have a positive velocity, and you wanted to speed me up, which way would you push on me? Would you push from behind or in front of me? If I'm walking this way and you want to speed me up faster, then I'm already walking. You want to accelerate me. Would you push me in the direction I'm walking or push against me, Chris? Behind me. In other words, if you were behind me and pushed, you'd push in the positive direction too, right? So to know to know for sure whether you're speeding up or slowing down, you have to know the velocity to begin with, the going velocity. And here's a general thing to keep it straight. If the velocity is positive and the acceleration applied is positive, that means it's speeding up in the positive direction. Right? So I'm going to make a little thing here. There's going to be only 4 options in 1D motion. So if you keep these straight, hopefully you remember it all year and this never gets you off guard somewhere when it matters in a problem. All right, so if we're going to say if V is positive, just write in parentheses beside a sign. I don't care what the actual magnitude is as long as it's positive. If V, and this is probably one, I don't care if you wrote down anything at this point, you probably want to jot this down somewhere. All right? Even if you put it on somewhere in the margin on the study guide, even would be a good idea on Squid. I'll try to condense it in the least amount of words as possible to make it nice and short and easy to remember. If V is positive and a given acceleration, usually we symbolize acceleration with a lowercase a, so I'll do that. If those are both positive, regardless of their exact magnitude, we just know their signs are positive, their directions are both positive, that represents speeding up. But can't I do the exact same scenario if I was walking that way? Let's say I start over here and something accelerates me by like somebody pushing me. So I'm walking this way. This way is the what direction? But with positive and negative. That way is positive, this way is negative. So I'm going this way. So my current velocity is negative. Who cares about what it actually is? What matters now is the sign. And if somebody wanted to speed me up and I was already walking this way to begin with, which way would they push me to accelerate me with their force? That way, right? From behind, pushing me and accelerating me in the negative direction if they push me from behind, right? Make sense? And that would still cause me to do what? Speed up or slow down? Speed up, right? So even though here's one example that even though my acceleration is negative, it's still going to represent speeding up, not slowing down. So this is the most important thing about today probably, is that just because something has a negative acceleration, does it have to mean slowing down? No. You have to consider what's going on in the first place. So that's also a way to speed up. So we're seeing a trend here. If both are the same sign, that means speeding up, right? Now there's two other options. They can be flipped, but then with just two possible signs, two possible directions, then the other two scenarios mustn't mean speeding up. They must mean, what's the opposite of speed up? Slow down. So let's go back to me walking in the positive direction to begin with. If I'm walking this way, and you want to slow me down, which way are you going to push? Towards what direction? Positive or negative? If I'm walking this way. Right? Negative. If I'm walking positive this way, right? But you want to slow me down, you've got to push this way, right? You got to do the opposite. And your push causes the acceleration, so that's the direction of the acceleration. Anytime the two signs oppose each other of what the current velocity is at the moment of acceleration, that will cause you to slow down. So there's two ways that could happen. It doesn't really matter the order we put these. So if my V is positive, like the one I just went over, and my A is negative, then that does represent slowing down. Does that make sense to everybody? As simple of the idea as it is, if you don't get this, and you just solely assume all the time a negative acceleration is a slowdown, you will get burnt on problems throughout the year. All right? Because you can't assume that unless you know what the velocity was at the moment. So I can flip that state, those signs on that, and it'll still mean slowdown. If the V is in a negative direction, if something's traveling negative to begin with, and then somehow a force comes on and applies a positive acceleration, that also means slowing down. It's just that if I only knew this, if I only told you, just like I started with today, earlier, if I only told you the acceleration and the sign of the acceleration, that's it, and I say, what am I doing, speeding up or slowing down? You would just have to say, I don't know. Because if I don't know what the thing was doing in the first place, just the sign of acceleration doesn't guarantee speeding up and slowing down. However, I'm going to make another statement. What we usually do when we get real problem heavy is if a problem doesn't tell me what direction I'm going, I'm going to make that the what direction. What makes sense? Use signs, not instead of right and left. Positive. So the question was, if a problem doesn't specify, if it just says a car's traveling, at 50 kilometers per hour, okay, or something like that along those lines, it gives you a speed. You're going to assume, if we're in 1D motion especially, which we are most of the time, you're going to assume that unless they tell me otherwise, I'm going in the positive direction, okay? And because we assume that most of the time, if you're going positive, and you slow down, your acceleration is going to be what? Negative. Most of the time, that's the case. Because most of the time, we just simply assume the direction we're currently traveling in a problem's positive unless told otherwise. So most of the time, yes, because of that, acceleration, a negative acceleration will represent a slowdown. That was quick. Okay. But it doesn't have to be that way. Just consider all this and remember this, all right? So the most important stuff from today is 3 ways to accelerate, all this stuff we just went over sign-wise, and the units. But one more thing before I let you have a little time to start is there's also a formula. And this is another formula I'm just going to straight up give to you, but very soon, after this week, we'll get to motion graphing and see where this formula comes from through graphs, and we'll prove it mathematically. Same with those simple ones from last week. We just kind of threw those at you. But remember, no formulas come out of thin air. Eventually, we figure out where they came from. Okay? So actually, though, this particular formula, I already wrote down the definition up here, right? A change in velocity over a time period. There's a symbol in math, hopefully most of you know, or have seen, that looks like a little triangle. What do we call that, and what does it mean in math? So there's a condensed way to write this formula, and it uses that, but we'll expand it even more. But I'm going to write it the condensed way with this symbol. What does a triangle represent in math? In algebra? Nobody knows? Technically, it's not a triangle. It's a Greek symbol called delta. That still doesn't explain what it means in math. The Greek symbol delta in math universally means changing. How many of you have heard that before now that I said it? If not, you need to remember this because this is a very important thing because there's a lot of change in stuffs in our formulas, causing the most condensed way to write those formulas with a delta. It's probably not the most useful way, but you need to understand what it means when you see it come up in a books or in notes or something like that. All right, so what did I just say word-wise? The definition of acceleration was a change in what over time? Velocity. So delta V means change in velocity. This is the mathematical way to define what acceleration is through a formula instead of words. This way is better. If all you understand is words in physics, you won't get very far. Because it's a math-based science. What proves it all is the math. All right? We'll give stuff in words, but the math is the most important part. So, and it was over time. Over means divide in math, right? Over t. And we'll eventually, when we do VT graphs, realize where this came from. Okay? But that's the condensed version using the delta. That means changing. A change in velocity, in the more expanded version, is the difference. That's a minus sign, the difference, right? The difference between an initial and a final velocity. All right? So I'm going to write equals, and I'm going to box this version of it because it's the most important one. We're going to subscript V's. VF means final velocity. VI, with the I subscript, means initial velocity divided by time. That's the main acceleration formula. VF minus VI divided by T. How many of you have ever watched like a car commercial, especially a like sports car commercial? They'll often say somewhere in whatever they're saying in that to advertise that vehicle, for some reason the standard is 0 to 60 for some reason. I don't know why, it just seems like it is. How many of you have ever paid attention to a car commercial that said, this car can do 0 to 60 in like 4 seconds? How many of you ever heard that like watching something? What they're really doing right there is in a roundabout way telling you it's acceleration, but not in a fully calculated way. The reason why they're not telling you it in a fully calculated version of it is because most people did not take any form of physics. And if we did give it to you in like miles per hour, if you were watching a car commercial, even if it was English units, and they came out and said, this car has an acceleration rate of 10 miles per hour squared, or something like that, who would have any idea what that meant, right? But we could understand the idea of acceleration through breaking it apart, which we're really doing right now in this formula, by saying this thing could go from 0 at initial velocity, right, to some final velocity, those aren't backwards, this is how they are in the formula, to 60 miles per hour in 4 seconds. We could understand that as a concept. Most people won't understand it as one big calculation by actually running the numbers, but we're going to go that far, and you need to understand that in here. All right, does that make sense to everybody? So that's 0 to whatever in whatever amount of time. That's really implying the acceleration rate that we can plug in this formula and get a single numerical magnitude rate for it. All right, so that's our main formula, and this one, again, will eventually prove it. You could even see in the formula, though, remember what I told you the most common unit is we'll run into. What is it again? Meters per second squared. So if you have some velocity, some ending velocity at the end of some time interval of 10 meters per second, and maybe your initial doesn't always have to be 0. It could be anything. You were going at some timed interval, okay? So you could have like 10 meters per second minus 5 meters per second is 5 meters per second, right? 5 meters per second divided by like 2 seconds is meters per second, right? So the units aren't made up either. The units are derived through the math, figured out. All derived means is figured out through the math. Yeah, the units themselves are treated like variables to condense them through that. So all that, everything we said right there is pretty much the minimum you need to know about acceleration right now. So with all this stuff in mind, you got a little bit of time to start the study guide. Don't forget, the link's still there. This is Still lesson 1, but the final part, I believe it's part E. So if you didn't like take in everything you needed to today from what I explained, all this same stuff is all within the reading. Try the best. It's not for right or wrong. Turn it in by class tomorrow. If you have to take a guess at something because you're not sure, that's fine. All right, just do your best on it. We'll go over all of them tomorrow. And then there's some concept builders on Wednesday, just to hit on some of this stuff. Old stuff and acceleration stuff. We're going to do primarily in class on Wednesday, Thursday. Tomorrow we'll wrap up acceleration, go over that study guide, and then a little quiz on Friday. Question?